This playlist deals with some aspects of Eurocode 2 version 2023. Watch this channel or playlist for further selected topics. In this video, we will talk about the clause 11, detailing of reinforcement, part 5, and it's about the anchorage of rebars. In the previous video, we have seen the anchorage of a straight bar. Now we will talk about the anchorage of bends and hooks. Section 1 is the control section. Starting from section 1 to the left, it's the anchorage length, and it must resist the force on the rebar, which is the cross area of the rebar times the stress or tensile stress in the rebar. The needed anchorage length from the end up till there, the needed anchorage length is must be equal or bigger or equal than the anchorage length that you obtain with formula 11.3, which is the anchorage length of a straight bar, minus 15 phi, and all of that has a minimum of 10 phi. The notation LBD is very confusing because LBD is already used for straight bars, anchorage of straight bars. So I prefer to add bend to LBD bend. So instead of LBD, it's LBD bend because this is the anchorage length for a bend or hook. And the LBD that we calculated with 11.3 for straight bars, just to make sure that it's not confused with the figure, then we should call this LBD tension, for instance. For a standard hook, it is a standard hook with an inclination of 135 degrees, and the straight portion is 5 phi. You can also have a standard hook of 90 degrees, and then you will have a portion of the straight line of 10 phi. This is not very clear. For 135 degrees, it's 5 phi, and 90 degrees, 10 phi. What is it for other degrees of bending, alpha bend, of other values of alpha bend? As from which alpha bend we switch from 5 phi to 10 phi. So this is not clear. It's quite confusing. And what will happen if alpha bend is, for instance, 180 degrees? Is it 5 or 10 phi? When alpha bend is 270 degrees, for stirrups, for instance, what is then the straight part? Is it 5 or 10 phi? So this is clearly not clear in the code. When you have a hook or a bend, then the concrete cover on the side, like it's indicated here, is called CYB. CD, which is the concrete cover, the nominal cover, used in formula 11.3 to calculate LBD or LBD tens. It's given in a formula, but now the formula changes again for the first or the third or the fourth time. Now it's the minimum of CS over 2, which was previously set so. Also CX, which is the cover on the X direction, CY, the cover on the Y direction, and now they added CYB, which is the cover in nor X nor Y direction. But what happened with the 3.75 phi or 3.5 phi? So this is omitted now. So this is quite confusing. It's not logic. 311.7 indicates the total length, LBD total, the total length of the rebar in a hook or a bend, and indicating the force, the tension force. And it gives you, for instance, for a standard hook of 135 degrees, the 5 phi again, with the phi mandrel, the diameter of the mandrel. This is for tension only. Huh? So anchorage of bends and hooks for tension only. Again, LBD is already used for straight bars. So why do they use it again for hooks and bends? So it's quite confusing, this. So I prefer to call this LBD bend. So now you are clearly sure that this is about this distance from there to there. Then they've said that, or in the codes says that LBD total, this one, must be bigger than LBD. I've added lengths because I want to make sure that LBD is the length calculated according to formula 11.3. So that's why I call it LBD tension. This is logic, and the total developed length should at least be or should be bigger than the length LBD for tension, and must be bigger than 10 feet. Okay, so that's no problem. That's condition 1. But now there's a condition 2, which says that LBD bend, which is this distance, must be bigger than LBD minus 15 feet. So you take the anchorage length of a straight bar, calculate it, and you subtract 15 times the diameter with a minimum of 10 feet in total. Then you have the anchorage length, needed anchorage length for a hook or a bend. Okay, but which condition prevails now? Is it condition 1, or is it condition 2? Is it NN? Does it mean that we have to fulfill condition 1 and condition 2? Or is it okay if we only fulfill condition 1 or only condition 2? So that's not very clear, but logic says you have to fulfill both conditions to be on the safe side. Then we do a little calculation. What I'm telling now is not in the code. So it's something that I developed myself, and it's the relationship between LBD total, which is stated here, and LBD bend, which is this. So now this can be easily verified with N is equals to the mandrel diameter is N times V, and alpha is expressed in radians. This is the bend alpha. But this 5 corresponds to this 5 phi, this one, this 5 phi. But we see now that for 90 degrees, it was 10 phi. So when you apply it for, make it applicable for alpha equals to 90 degrees, then you should put here, instead of 5, you must put 10. Again, like I said before, there's a problem. As from which alpha is the 5 phi changing into 10 phi? We don't know. You can now, with this formula, you can easily see that is n, if n plus 1 times alpha min 1 is smaller than 20, for n equals 7, alpha must be smaller than 200 degrees, and then condition 1 is dominant. So for this, condition 1 is dominant. So that means that this is the dominant factor. So why introducing condition 2? Because this is always dominant for n equals 7. Or you can say that this is dominant for the minimum mandrel diameter. And let's put this very clear. Alpha smaller than 200 degrees. For most cases, it's ridiculous because alpha cannot be bigger than 180 degrees. Only for stirrups, when you go really 270 degrees or something like that, but that's an exception. So this means always. Now, if you look at alpha 135 degrees, which is a standard hook, and alpha 90 degrees, which is a standard hook, well, condition 2 is dominant, this condition, only if the mandrel diameter is bigger than 7.5 feet, or in this case by 90 degrees, if the mandrel diameter is bigger than 3.7 times the diameter. Now you know that the minimum diameter for a diameter, bar diameter, smaller than 16 is 4 feet, and for a diameter bigger than 16, it's 7 feet. So you see clearly that condition 2 here is never dominant if you use a minimum mandrel diameter. I think this needs some more explanation. Why is this the case? For compression, and we are still in anchorage of bends and hooks, this time for compression. Again, it's indicated on the figure that this is LBD, which is again very confusing. So I suggest that we should call this LBD bend. And the definition here of this portion is the projected first straight segment. Now this definition is not corresponding with the figure, because in the figure you have curved segment in it. So why make a definition which is not corresponding with the figure? So I've chosen to follow the figure and not the text. For compression, LBD bend must be bigger than LBD, which is logic, and must be bigger than 10 phi. And this in the case when the nominal concrete cover is smaller than 3.5 phi. I put it behind brackets because it's not only Cx and Cy that plays a role, but also Cyx, which is the cover on the portion here. And when this CD is bigger than 3.5 phi, then you can use this formula. Now, you see this was condition 1, this was condition 2. Now suddenly they say which condition prevails, depending on the concrete cover. This is not what we have seen in the previous slide. So again, it's not consistent anymore. But this is for compression, so this is a total different game. Just bear that in mind. Anchorage with welded transfer reinforcement, that means, of course, a mesh of reinforcement, for instance. Then you see that LBD is indicated on the left of the control section 1, make it an equilibrium with the force, the surface, the cross section of the bar times the tensile stress in the bar. Again, I propose you should call this LBD weld instead of LBD to avoid confusion. When the transfer reinforcement diameter is bigger than 0.6 times the diameter of the bar, then when you have a support, then you should anchor it over a distance LBD on top of the over the support, which is logic and which we have done previously. The transfer reinforcement, the distance to the edge of the support must be bigger than 50 millimeters. When the diameter of the transfer reinforcement is smaller than 0.6 times the diameter of the bar, then we have different transfer reinforcements spaced at the distance between 50 and 100 millimeters, which is quite dense. A spacing of 50 millimeters, I will not recommend it. This is quite ridiculous. Your concrete cannot go through it. So because the minimum value is 40 millimeters. So this is very, very dense. So an S equals 100 is also dense. And then again, the first bar must be at least 50 millimeters from the edge. Also, you can only use this method with welded transfer reinforcement if the diameter is smaller or equal to 16 millimeters. Then the anchorage length LBD weld equals LBD tension. It's the anchorage length according formula 11.3 of straight bars minus 15 phi. And it must be bigger than 5 phi. This is strange. In all other formulas, it's bigger than 10 phi. So why suddenly for a welded transfer reinforcement, the minimum anchorage length is 5 phi? It's a little bit strange. Now, about anchorage with U-bar loops, you have a U-bar loop, you have two forces on the loop. In this example, the force F1 is equal to the force F2. Then you have the anchorage length LBD. This is again confusing, so we call it LBD loop. But is this LBD running from cross section 1, control section 1 up till the end, and that's it, LBD, or is it the total length, LBD? It's not set, it's not specified. First, it says that for U-bar loops subjected to pure tension, anchorage may be considered to be provided if the loop details comply with 11.3. So if you comply with minimum mandrel diameter and so on, then you can regard this U-bar loop as fully anchored. That's what it says here. So you don't need, LBD is in fact 0. So if you make this loop consistent according to the rules with a phi mandrel at least equal to the minimum mandrel diameter, then they say it's fully anchored. Okay, why not? And then it says, alternatively, why? Why is there an alternative? Alternatively, the LBD loop, which is from there to there, must be bigger than LBD for straight bars minus 20 phi and must be bigger than 10 phi. This is not very clear. Why should we have the option between those two? Or it is fully anchored or it is not. It's one of the two. Also, like we mentioned before, LBD, is this about half of the length or is it about the total length? It's not clear. And secondary, is this now in vertical plane or in horizontal plane? Is it also valid for horizontal when this is the horizontal plane? Because this is often used in practice. So it should be stated that this is both horizontally, vertically, or in any direction. Now we will talk about the anchorage of headed bars in tension. A headed bar is a rebar with a head on it. The head can be circular, it can be rectangular, or it can be rectangular. So it's often used in punching reinforcement, punching shear reinforcement. The anchorage length is then LBD. We should say LBD head, of course, because otherwise it's confusing again. The diameter of the head is VH, and the force in function of the X on the start of the head, it's sigma accent SD times the cross section, and at the end it's sigma SD. So because this is our control section, and from there on you can count on the anchorage of the bar with a tensile stress of sigma SD. You see two portions in it, which is LBD, the length of the rebar gives you resistance, and the head gives you an additional resistance. So the total anchorage is the sum of the two. There are some conditions for the head, but this should be very clear. Then the definition of AY, AX, and SX, we've seen that before. Make your attention that SX is now not the clear distance, but the center-to-center distance. So this changes in every application. Sometimes SX is the clear distance, and sometimes it is the center-to-center distance. Confusing, yeah, that's for sure. A tensile stress in the reinforcing bar sigma SD equals to 435 megapascal may be considered to be developed without additional anchorage length. So if you have a headed bar in tension, then you can consider that the tension in the rebar can be developed of 435 megapascal without taking into account LBD. That's not needed. It's just the head gives you this resistance. But why 435 megapascal? This is strange. You have other qualities, steel qualities of rebars going up to 700. So it's very strange that suddenly they take 435. So in an accidental situation, yeah, maybe then it's not possible, because in an accidental situation, you can go to 500 megapascal in this case. Anyway, they limit it to a specific number, 435 megapascal. But you can only calculate on that when you have to fulfill on the following conditions. The diameter or equivalent diameter of the head must be smaller than 4 times the thickness of the head and must be bigger than 3 times the rebar considered. Okay, that's a normal condition. Concrete quality must be bigger than 25 megapascal to avoid crushing. The diameter must be smaller than 25 millimeters, because otherwise the force will be too big. DDG is 32 millimeters, must be bigger than 32 millimeters. SX, the distance center to center of different bars anchored in line, must be bigger than 4 times AY, must be bigger than 4 times this concrete cover. AX must be bigger than 2AI plus 1.2 VH, okay? And when this is bigger than 3 times the diameter, of AI must be bigger than 3 times the diameter for an uncracked section, and it must be bigger than 4 times the diameter for a cracked section. Calculating concrete in ULS, one of the conditions is that you make is that concrete is cracked. That's it. Concrete is cracked. So a situation where concrete is not cracked, it's not quite often that you can use this condition. It can be at the support, for instance. But anyway, when you are not sure because you don't know it in advance, not always, then you take 4 phi. AY must be bigger than 4 phi, which is feasible. And then the last condition is that AX must be bigger than AY. Now, on first sight, AX must be bigger than 2AI plus VH, which is positive. So why introducing this condition? But when you think about it, this condition means only that in all those formulas which is stated here, AX is the biggest. So it's the biggest of AX and AY. So it's the biggest of this and this. So when AY gets bigger than AX, then you have to inverse the formulas. Huh? So we have the headed bar in tension. We have seen that the different the force, the development of the force in this anchorage. Sigma accent as D is then given by this formula 11.8. So this is at the beginning. So this is the resistance that you can develop. The pH squared divided by 4 is the cross section of the rebar times the tensile stress sigma accent as D is the maximum force that you can develop by the head only, because it's at the beginning. Then you have this formula with KHA equals, it's just a factor like it's stated in formula 11.9. You see that if VH equals V, then this part is 0. And then you will see here, it must be smaller than 0, which cannot be the case. So it means that if your head is the same size as the rebar, that your resistance of the head is 0, which is completely logical. The part is for uncracked section 11 and for a cracked section 8. And AD is the nominal value of the distance between the bar and a free surface. Okay, so again, a kind of a concrete cover. Let's look now at the nominal value of distance AD. For a single bar near to an edge, AD equals AY. And not AX. So this is not clear. Why is it AY? Anyway, let's suppose this is correct. For a corner bar in a corner, when AX, now AX comes into the game. When AX is bigger than 2 times AI plus 1 point times VH, then AD is AY. Okay, that's clear. And when AX is smaller than this value, then AD is a combination of AY, AX, and VH. For multiple bars with a distance Sx, when Sx is bigger than 4 AI and AX is bigger than 2 AI, then AD equals AY. And in other cases, group of bars along an edge, when the distance Sx, the distance center to center, is between VH and 4 AI, then AD is given in this formula. Now, most of the time when you use a headed bar in tension, it's along an edge. It's one connection after the other along an edge. So this will be used in most cases. Formula 11.10. Now we will explain a procedure how to calculate an anchorage of a headed bar in tension. You start by calculating sigma SD, which is of course the total force that you want to obtain divided by the cross section of the bar. Then you take step 1, you calculate the develop length needed for a straight bar with the tension force sigma SD. You calculate with formula 11.8 the sigma accent SD, this one. Then you calculate the develop length or not the develop length, but the anchorage length needed, LBD needed for sigma accent SD. And in step 4, with formula 11.9, you calculate the anchorage length LBD. And LBD, this one, is equal to the difference between the two anchorage lengths based on sigma SD and based on sigma accent SD, and multiplied by a safety coefficient of 10%. This is only for the force in the anchorage length, which is there, from there. And when used for shear or confinement reinforcement, anchorage should only rely on the head only, so only on sigma accent SD. We will give in the next video an example how to deal with that. Finally, the anchorage of bonded post-installed bars can be interesting when you have an existing building and some new elements will be built next to it, or then you also need some anchorage of bonded post-installed bars. Control section 1, you have LBD. I prefer not to call it LBD to avoid confusion, but call it LBD pi. And it must resist the force cross section of the bar times the tensile stress. And LBD pi post-installed, LBD post-installed equals LBD divided by a coefficient. It must be bigger than 15 times V. And this coefficient is between 1 and 0.7. It's the bond efficiency factor. In Annex C8, you need some more information how to calculate the bond efficiency factor. This is valid for FCK smaller than 50 megapascal. You cannot go higher. And sigma SD must be smaller than 435 megapascal.